In chemistry, the word spontaneous has a very specific technical meaning, and it refers to processes that are able to proceed without any outside intervention, or without you putting any outside energy into the system. So if you look at the example on the left-hand side, you have a glass bulb connected to another glass bulb. The left-hand side bulb is empty, it's evacuated, it's under vacuum. And the right-hand side has 1 atmosphere worth of gas filled in it. When you open the valve, the gas in the right-hand side in bulb B will spontaneously move to fill bulb A as well. Remember, one of the general properties of a gas is that it expands to fill its container. As soon as you open the valve, you have A and B combined into a single container, and the gas will expand. You don't have to push any of the gas molecules along. They'll simply expand on their own. One point to note is that processes that are spontaneous in one direction can be non-spontaneous in the reverse direction. So all of that gas moving from bulb B into the open container that is made up of both bulb A and B, that happens spontaneously. But once you've got the gas spread out, it won't spontaneously move all back into bulb B. That's very unlikely to happen. The same thing can be true for the example on the right-hand side, a nail rusting. A nail is made largely from iron, and it can spontaneously oxidize to form iron oxides that make up what you would think of as rust. And this will happen over time spontaneously. You don't have to put any effort into it. It will happen all on its own. On the other hand, a rusty nail doesn't spontaneously convert back into unoxidized iron. Some spontaneous processes are only spontaneous at a certain temperature, or within a certain temperature range. So if you consider the example of water converting between liquid and solid, that is, if you look at the example of liquid going to ice or ice going to a liquid, you can have processes that are spontaneous at certain temperatures. So for the conversion between liquid and solid water, above 0 degrees Celsius, ice spontaneously melts. You don't have to do anything to the ice. As long as the temperature is above 0 degrees Celsius, the ice will automatically convert. On the other hand, below 0 degrees, the reverse process is spontaneous. Liquid will spontaneously convert into ice. This kind of temperature-dependent spontaneity is something that's fairly common, and we'll encounter it again later in the chapter. Entropy is a term that was introduced in the 19th century by a scientist named Clausius. Clausius was convinced that the ratio of the heat transferred at a certain temperature during a process was important. And it was eventually discovered that entropy, given the symbol S, was proportional to that heat to temperature ratio. And entropy can be thought of as a measure of the randomness of a system. And this randomness is very much related to both the modes of motions that molecules can undergo, and it's also related to the spontaneity of different processes. So like other forms of energy, total internal energy, enthalpy, things like this, entropy is a state function, which means that it is path independent. The change in entropy only depends on the initial and final conditions. So for a process that occurs at constant temperature, an isothermal process, the change in entropy is going to be equal to the heat transferred divided by the temperature. So we can combine these two equations and we can get delta S equals Q over T. Now that we have an equation that allows us to calculate a delta S, we can do an example. So elemental mercury, Hg, is a liquid at room temperature, and the normal freezing point for mercury is minus 38.9 degrees Celsius. Its molar enthalpy of fusion is 2.29 kilojoules per mole, and we want to know what is the entropy change of the system when 50 grams of mercury freezes at its normal freezing point? Well, to start with, we're going to need a Q. We're going to need a heat. We're looking for delta S. We need Q, and we know what the temperature is. We know that the freezing point is minus 38.9 Celsius. So we need to find Q. Well, this means we can use calculations very similar to those we used in Chapter 5, the thermochemistry chapter. We have 50 grams, and we can look up the molecular weight of mercury. That molecular weight is 200.6 grams per mole. We can use the mass and the molar mass to find the number of moles of mercury. And we can use the delta H of fusion, the delta H for the interconversion between liquid and solid, to find the amount of heat that gets transferred in order to freeze 50 grams worth of mercury. And we find that 0.571 kilojoules are transferred. And it's probably important to note that fusion is melting, and we're talking about freezing, so we should add a negative sign to make sure the direction is clear. So in order to freeze, you have to lose heat energy. It's an exothermic process, so you need to have a negative sign for your heat transfer. In general, we want to work with standard units, so it would be worthwhile to convert this number to joules. We should probably do something similar for our temperature and convert it into Kelvin. And now we can calculate our delta S. And we end up with a value of minus 2.44 joules per Kelvin. This is a pretty common set of units to see for a delta S, joules per Kelvin. And we found the delta S for this process, for converting 50 grams of mercury to solid mercury at the normal freezing point. We can also talk about one of the laws of thermodynamics that states that the entropy of the universe increases for spontaneous processes, and it doesn't change at all for reversible processes. So we can convert that into an equation. And this second equation really means that all spontaneous processes, which are irreversible, are going to increase the entropy of the universe. And for anything that is reversible, so non-spontaneous, you're going to have no change in the entropy for the universe.